Every time a Falcon 9 booster lands successfully, SpaceX saves $62 million. Every time it fails, that money falls into the ocean. I asked a simple question. Can we predict which landings will succeed? The answer is yes, 94.4% accuracy. But the accuracy isn't the story. The insights are. Boosters with 5 or more flights achieve 100% landing success. Experience isn't just valuable, it's everything. LEO missions succeed at 78%. GTO missions? 52. Same rocket, same engineers, different physics. The orbit burns more fuel, leaving less for the landing burn. This is what success looks like. And this is what happens when something goes wrong. The margin between them is measured in milliseconds and meters. $103 million. That's the difference between building a new booster and reusing one. Multiply that by 90 launches per year. That's why SpaceX owns 60% of the commercial launch market. I built this from scratch. Data collection from SpaceX's REST API and Wikipedia tables. 17 feature columns. 90 historical launches. SQL analysis for pattern discovery. Feature engineering with temporal variables, rolling success rates, and booster age calculations. 10 SQL queries revealed patterns that weren't obvious. Reused boosters outperform new ones. 77.8% versus 58%. Proven hardware beats factory fresh every time. I trained 6 models. XGBoost, LightGBM, CatBoost, stacking ensembles. All the modern techniques. But the winner? Support Vector Machine, a model from the 1990s, on a dataset of 90 samples, simpler one. That's not a failure of advanced methods. That's a lesson about matching model complexity to data size. SHAP analysis revealed what actually drives predictions. Landing pad infrastructure, 0.681 importance. Reuse count, 0.657. The model learned what SpaceX engineers already knew, but now we can quantify it. Geography matters too. KSCLC 39A sits 3.89 kilometers from the coastline, 15 kilometers from the nearest railway. That's not a coincidence. That's calculated safety margins meeting logistics optimization. And that dip in 2017? It looked like failure. It was actually the Block 5 transition. Hardware upgrades caused temporary regression before breakthrough. Understanding that pattern changes how you interpret the data. I didn't just analyze history, I deployed a live prediction system. Enter launch parameters, get a probability, make better decisions. This project covers the full pipeline. API integration, web scraping, SQL analysis, exploratory visualization, feature engineering, model training with cross-validation, SHAP interpretability, geospatial analysis with Folium, and a production web application with 3.js animations and responsive design. But beyond the technical work, there's a bigger insight here. Reusable rockets aren't just an engineering achievement, they're a data problem. And data problems have data solutions. SpaceX made humanity's future in space economically viable. I wanted to understand how. This is what happens when you treat rockets like a machine learning problem.